Hi everyone, welcome to Chemical Bonding YouTube channel. Today we will discuss about 5 questions taken from organic chemistry, and that will be very helpful uh, for upcoming CSIR-NET and GATE exams. So let's start. Question 1. So in these questions, one compound is given and it is treated with sodium ethoxide base. So in that case, when we see in a given compound, if there is any living group like bromine, bromide means halogen, and OTS, OMS, etc. And if there is present any beta hydrogens, means this is alpha hydrogen containing the bromine atom or any living group like OTS, OMS, and the adjacent carbon contain any hydrogen that is called beta hydrogen, then we can think about elimination reaction. So if and obviously if there is they if this compound is treated with base, so in that case we can think about elimination reaction, but there are many types of elimination reaction. So using base we can think about E2 elimination reaction or ion CB elimination reaction or Hoffman elimination reaction. So if there is given neutral living group like bromide, OTS, OMS, and if there is present beta hydrogen, so we can think about E2 elimination. If this living group is poor in nature, means fluoride, even it is OH means hydroxyl, and if this beta hydrogen containing carbon, this beta hydrogen containing carbon also containing some electron withdrawing group, so that after abstraction of this beta hydrogen, this negative charge can stabilize by that electron withdrawing group, then we can think about ion CB mechanism. In the other case, if that living group is a positively charged living group like tertiary ammonium like living group, then we can think about Hoffman elimination reaction. So in this case, bromide is a neutral and moderate living group, and there is present beta hydrogen, so we can think about E2 elimination. Since in beta carbon position there is no electron withdrawing group, so that after abstraction of this proton, that negative charge can be stabilized by that electron withdrawing group. If there is present any electron withdrawing group, then we can think about ion CB mechanism. But in this case, that E2 elimination is possible. So for E2 elimination, we all know, for E2 elimination, the primary criteria between that for the elimination, the primary criteria is that the living group and that beta hydrogen should be in anti-periplanar orientation. Means between their the angle between the dihedral angle between them should be 180 degree. So the given compound is a cyclohexane, substituted cyclohexane. So we will draw it a we will draw the compound in a chair form. So in chair form, see, in this form, bromine and also that methyl group is axial positions. If it flips, it contain this type of uh, if it flips, then it transforms in another conformer where that bromine and CH3 group rest in a equatorial position. This conformer is more stable than this conformer. But see, in this conformer, this bromine group and this beta hydrogen, there is beta hydrogen, this leaving group, and this hydrogen and this hydrogen, there this two hydrogen and this bromine group, there are no such condition, means no favorable condition for elimination, that is anti-periplanarity. But this is less stable conformer, still it flips into this conformer, though it is less stable, but it flips into this conformer, and in this conformer see that bromine atom leaving group and this deuterium is perfect anti-periplanar orientation, and in this conformer the elimination will occur, not in this conformer. In equilibrium condition, the percentage of this conformer is very low. Still, for elimination to occur, this compound should be transformed into this conformer so that the bromine group and that beta deuterium rest in a anti-periplanar orientation so that elimination can take place. So this is more stable conformer, this is less stable conformer. In less stable conformer, anti-periplanar between the beta deuterium and bromine leaving group is possible. That's why an elimination occur in this conformer, and we will get this type of a cyclohexene compound. So this is the product. The product should not contain any deuterium. Let's see. Option 1 contain deuterium, option 2 contain deuterium, option 3 there is no deuterium, double bond adjacent position, methyl below, hydrogen above, 4, two options, deuterium, deuterium. So option 3 is correct. See, double bond adjacent position, methyl group is below, hydrogen is above. Option 3 is correct. So remember the point that for primary criteria for a A2 elimination reaction, that the anti-periplanar orientation of the leaving group and beta hydrogen. Let's move to the next question. So in these questions, for different types of in-ion compound is given. In-ion compound means in same compound on triple bond and on double bond is there. In and ion. So in the questions, the anion that produces a chiral compound upon treatment with Lindlar catalyst. So chiral compound. So if we treat this compound with Lindlar catalyst, then which one will give chiral compound after treating with Lindlar catalyst? Chiral compound means there should be at least on chiral center. There should be at least on chiral center. Means that center containing different types of groups. So let's see each of the compounds, and we know one things that Lindlar catalyst, we know one thing that Lindlar catalyst is used for the hydrogenation of alkynes to alkenes. It is used for hydrogenation of alkynes to alkenes without further uh, hydrogenation of the alkenes to alkane. So it only hydrogenate alkyne to alkene. But there is one point to be noted that Lindlar catalyst hydrogenates alkyne in such a way that the product alkene should be cis or jet in nature. So after hydrogenation, the alkyne geometry should be cis, or you can say jet. So this is Lindlar catalyst, palladium calcium carbonate or sometimes palladium barium sulfate with lead diacetate. and this is quinoline. This whole mixture is called Lindlar catalyst. So see, in ine 1, after treating with Lindlar catalyst, obviously hydrogen should be there, hydrogenation. So no chiral center means there is no chiral center. See, there is no chiral center. Compound 2, if we treated with linear catalyst, this is a transalkene, and this alkene, yeah, this alkene should be in cis, should be transformed in a cis alkene. This alkyne should be transformed in a cis alkene after treating with linear catalyst. So this is a transalkene, this is a cis alkene, hydrogen methyl. So there is on chiral center. So this compound is chiral. Let's check other. So this compound also, when we treated with linear catalyst, then there is no chiral center. In the fourth case, this alkyne transformed into alkene, and this alkene and this alkene are same. This alkene and this alkene become same. So there is no chiral center. So only compound 2, that ine, after treating with linear catalyst, give a chiral compound that contain one chiral center. This is E alkene, or you can see trans alkene. This is Z alkene, or you can see cis alkene. This alkyne transformed into cis alkene after treating with linear catalyst. And on point, I have to be mentioned that if you treated the alkyne with sodium and liquid ammonia, that is Bart's reduction. In that case, we we only get trans alkene. So alkyne give cis alkene when we treated with linear catalyst. Alkyne give trans alkene when we treated with sodium and liquid ammonia. That is Bart's reduction. So the correct option in this case is 2. This 2 is the correct answer. Let's move to the third question. So in this questions, thiophene reacts with formaldehyde in presence of HCl. So it's a simple question. So first formaldehyde, the oxygen protonate to release a Cl minus, and this thiophene react in this way. The two position react in this way to form a two thiophene 2 methanol type compound. CH3 OH methanol, here CH2 OH thiophene 2 methanol compound. And in presence of acid means there is HCl in presence of acids. This OH again protonate, and this Cl minus from that HCl. In this case, H plus from HCl protonate that OH, and that Cl minus attack in that position, and water molecule is released. This position is somewhat like benzyl position, or you can say, yeah, benzylic position, and it is prone towards SN2 type reactions. So finally we got this product, CH2Cl, two position thiophene, two position CH2Cl. So the correct option should is this option 2. Question 4. So this is a somewhat conceptual question. So I am trying to explain everything regarding these questions. So try to understand this question. Monochlorination of methyl cyclopentane by chlorine at low temperature in presence of light gives major product. So we all know that how in presence of light chlorination or halogenation occurs in alkane molecules. So first this CCl bond break to provide chlorine radical. Then this chlorine radical abstract on H from this alkane and on alkyl radical formed. This alkyl radial further react with another uh, molecule of Cl2 to release one Cl radical. So in this case, see, one alkyl radical is formed, and in that case, if the alkyl radical is more stable, it will easily form. If the alkyl radical is more stable, then it is easily formed. So let's see the compound. This is methyl cyclopentane. Methyl cyclopentane. So there are four types of hydrogen. These three hydrogens are 1 degree. These four hydrogen are 2 degree on type. These four hydrogen are 2 degree on type. So actually three types of hydrogen: 1 degree, 2 degree, and this hydrogen is tertiary, or you can say 3 degree. So but in these four hydrogen are different from this four hydrogen, because one methyl group is there adjacent to this four hydrogen. So so by observing this mechanism, you can say the abstraction of this hydrogen is more favorable, because when chlorine radical abstract this hydrogen, there occur a 3 degree radical, and that is more stable. And then if this hydrogen is abstracted by chlorine radical, then a 2 degree alkyl radical is formed. If there is if the chlorine radical abstract with hydrogen, there is 1 degree alkyl radical form. So you can easily say that this is the major product in this reaction, but it is not the case. So in this case, not the stability factor. In this case, statistical factor dominate. Statistical factor dominate means when chloride radical form, chlorine break into chloride radical in presence of light, then chloride radical is so unstable. So we can say it is less selective. It is so reactive. So it has no time to select particular hydrogen and abstract that hydrogen to form a stable radical. So there is present 4 into 4, 4 and 4, 8 2 degree hydrogen. So it will see there are lots of 2 degree hydrogen around this chloride radical. It will abstract this hydrogen fast, means 2 degree radical fast. And it will also see there are 3 degree, there are three hydrogen that are 1 degree, and it will abstract also this 1 degree hydrogen before that 3 degree hydrogen. So there is a chance, statistical probability for abstraction of hydrogen is more for this 2 degree hydrogen. There are 8 2 degree hydrogen. So it will abstract first the 2 degree hydrogen, because there are a lot of 2 degree hydrogen. It sees after forming radical chloride radical sees there are a lot of 2 degree hydrogen, means 8. So it will abstract that hydrogen only, not that tertiary hydrogen. So it has no time to select on hydrogen and give time. After abstraction, it will become, after abstraction of that hydrogen, the more stable alkyl radical is formed. It has no time. When the chloride radical form, it will immediately see that there are lot of 2 degree hydrogen, means 8 2 degree hydrogen. So it will abstract this hydrogen. So that's why I call in this case statistical probability dominant. So there are two types of 2 degree hydrogen. These four are same kind of 2 degree hydrogen. These four are same kind of 2 degree hydrogen. So formation of formation of these two compound, is, probability of formation of these two compound is same, because These are 2 degree hydrogen, but different type of 2 degree hydrogen. Number of hydrogen are same. So at this position and at this position, methyl and this on 2, methyl and this on 3. So 1 2 and on 3, these two alkyl radical form in equal amount, but see, this CH3 and chlorine is on 3 position, so there are less steric crowding or steric repulsion, so it is more stable compound, and we can call it is thermodynamically controlled product. And it is measured when the temperature of the reaction is high. This is on to methyl and chlorine is on to position, so this alkyl radical is called KCP, kinetically controlled product. There is some steric repulsion between this CH3 and Cl, so this product mm, is less stable than this, so this is called kinetically controlled product and it is measured in low temperature. So if in these questions they are not mentioned any temperature, by chlorine only monochlorination of methyl cyclopentane by chlorine in presence of light gives major product, then we can say that this 1,3 is the major product, but they mention at low temperature, so that's why that kinetically controlled product become the major product. So this is the major product in this case. I hope you guys understand this concept, why the stability factor is not predominant here, statistical factor is predominant here, why this chloride radical is unstable. Chloride radical is so unstable, so it has no time to select a particular hydrogen and abstract that, and and give time to the alkyl radical to give time to form more stable alkyl radical. It will form immediately, it sees that there are lots of hydrogen around it, so it will abstract that hydrogen. That's why it will abstract 2 degree hydrogen. Since there are two types of 2 degree hydrogen, the formation of 1 2 and 1 3 compound are probability same, so they are formed in equal amount, but this is stable on 3 position, less steric repulsion. This is less stable than this 1 2 position, some amount of steric repulsion. This is formed in high temperature, major product. This is formed as major product in low temperature. In this question, they mentioned that low temperature, so this option 3 is formed as a major product. So option 3 is correct option. So question 5. So it is a simple basic chemistry. Means I think can we see we used to see normally this type of questions, this type of chemistry in 12th standard or in undergraduate standard. So this is a table, match the compound given in the list on with their characteristic reaction given in the list 2. Select the correction option, select the correct option. So list on is a primary amine, it's an alkyne, terminal alkyne, it's a ester, it's a 2 degree alcohol. So alkyne hydrolysis with KOH and chloroform produces bad smell. It gives white PPT with ammoniacal AgNO3. With Lucas reagents, cloudiness appears within 5 minutes. I think you all know that primary amine react with potassium hydroxide and CaCl3. They give isocyanide that is bad smell. That has bad smell, and we all know that ester became hydrolyzed in presence of alkaline, means sodium hydroxide. So but we have confusion about this Lucas reagents, and yeah, we also know the Lucas reagent. I think from in 12th standard or in undergraduate standard we saw this kind of reagents in uh, textbook. So still this is carbylamine reaction. So primary amine in presence of potassium hydroxide and chloroform form isocyanide, and that has bad smell. So this is called carbylamine reactions. This is the mechanism. First, dichlorocarbon is formed. Then this amine attack that carbene carbon, and eventually a proton transfer is occur. Then this OH minus abstracts on hydrogen, and in this case still again an alpha elimination occur. So now this lone pair of nitrogen push that electron to carbon side. So N plus triple one C minus. This is the mechanism of carbylamine reaction. So primary amine A matches with 2 with KOH and CaCl3 produces bad smell. I have to mention one thing that when we use aniline, CaCl3 NOH formed isocyanide, isocyanobenzene, carbylamine. This is carbylamine reaction. If you used phenol in presence of CaCl3 and NOH followed by acid workup, then we got salicylaldehyde. This is Riemann-Tiemann reaction. So aniline, same condition, chloroform, sodium hydroxide, isocyanobenzene, carbylamine reactions, phenol, chloroform, NOH followed by acetic workup. We got salicylaldehyde, orthohydroxybenzaldehyde. So that's called Riemann-Tiemann reactions. And Lucas reagent. So by this reagent, we can differentiate different type of alcohol: 1 degree, 2 degree, 3 degree. So normally 3 degree alcohol react with Lucas reagents. It is anhydrous zinc chloride in concentrated HCl solution. It is a solution of zinc chloride that is anhydrous in concentrated HCl. So first this zinc chloride coordinate with the OH group, and then this bond break form a carbocation. So in this case that this 3 degree carbocation easily formed, and immediately white turbidity appears. So also in 2 degree case, ZnCl2 and HCl, 2 degree case, that carbocation 2 degree is less stable than 3 degree. So white turbidity appears after 10 minutes, or you can say within 5 or 10 minutes we can see the turbidity for 2 degree. But if we use primary alcohol, then and in room temperature we can't see any turbidity. So if we heat long time, then that solution become turbid. So with Lucas reagent, 3 degree alcohol react immediately and form a white turbidity. The solution become white turbid. So we can easily say that is a 3 degree alcohol become, because the generation of 3 degree carbocation is more favorable than 2 degree, and 2 degree carbocation is more favorable than primary carbocation. So for 3 degree Lucas reagent, reaction with Lucas reagent, 3 degree alcohol immediately react, 2 degree alcohol react within 5 or 10 minutes. For primary alcohol, normally in room temperature it does not react, but if we heat for some time, then the solution become turbid. So this D means that secondary alcohol 4 match with 4 with Lucas reagent, cloudiness appears within 5 minutes. So 5 to 10 minutes for secondary alcohol, within 5 to 10 minutes the turbidity appears. So D matches with 4, A matches with 2. Now we all know that this ester should be matched with alkaline hydrolysis. We all know that in presence of alkali, ester hydrolyze with alcohol and acids, carboxylic acids. Now B acetylene, only one option is remain, 3 gives white PBT with ammoniacal AgNO3. So this is a functional group test. Functional group test means terminal alkyne test. So we all know this functional group test. If you use copper chloride with ammonium hydroxide's terminal alkyne gives this type of uh, copper salt, and the color of the solution become ppt red ppt form. If we use silver nitrate in place of ammonium hydroxide, then white ppt appears. So this silver salt of form. And if we use sodium in ether and react with this acetylene, then uh, then evolution of hydrogen is appear, means hydrogen gas is evolved if we use sodium in ether. So these three reactions are functional group test for terminal alkene. So now see the options. So A matches with 2, B matches with 3, C matches with 1, and D with matches with 4. So D4, C on, B3, and A2. So correct option is option 3. Correct option is option 3. So I think all of you understand. So among these 5 questions, the chlorination was somewhat conceptual. I think you all understand. So thank you for watching this. Stay safe, stay healthy.